All right, so here's what happened. Here's part 2 of the review. I'm recording this at a later time. I recorded this entire problem and then it glitched, and I am not going to rewrite this entire problem because I am lazy. So I'm just going to kind of talk through what I did here. So sorry about that. Anyway, for 9b, which is where we left off on the review, taking the derivative of finding dy dx for y to the fourth cosine inverse of 2x plus 5 equals e to the y squared plus x squared. For this part here, you have to do product rule, so that's what happened here. I did product rule. And then you have your f prime g, and then what happened here, this was a plus, because it's product rule, it's plus, but because this was a negative, I went ahead and just made it a minus here. So g prime f, and then on the other side, the derivative of e to the y squared is 2y dy dx, and then a derivative of, and then e to the y squared, and then derivative of x squared is 2x. So then I went ahead and moved everything with the dy dx to the left side. Everything else went to the right side. That's what happened here. Then I factored out the dy dx's, and then I was down here. And then I think when I pause this right now, it's going to skip back to when this was all blank, and I think I finished it out there. So sorry about that. I don't know what happened. I guess sometimes Biddle's weird like that. So sorry there, my Apple Pencil died. We are back on. All right. So we are dividing by all of that on both sides. And this cancels, leaving us with dy dx equals 2x plus 2 over the square root of 1 minus 4x squared all over 4y cubed cosine inverse of 2x minus 2y e to the y squared. And that is your final answer. All right. Now we're looking at 9c. With 9c, once again, we are finding dy dx. And looking at this, we're going to have to do quotient rule here, where this guy on top is f and the one on bottom is g. So f is ln y. F prime is 1 over y dy dx. G is y plus 2. G prime will be dy dx. So differentiating both sides here, this is going to be for quotient rule. Remember, it's f prime g minus g prime f all over g squared. So f prime 1 over y dy dx times g, y plus 2, minus g prime dy dx times f, which is ln y, all over g squared, so y plus 2 quantity squared. Oops. And then minus derivative of negative 5x will be minus 5. Derivative of e to the x cubed will be 3x squared. That's the derivative of the exponent, times e to the x cubed. So now we have some troubleshooting to do. First things first, we need to get rid of this y plus 2 quantity squared in the denominator. So we have to multiply both sides by y plus 2 quantity squared. When it gets distributed to this fraction, it will cancel, but it also will get distributed to this negative 5. So we have 1 over y dy dx times y plus 2 minus ln y dy dx minus 5 times y plus 2 quantity squared equals 3x squared e to the x cubed y plus 2 quantity squared. We need to get the dy dx's by themselves, and the good news is this won't be that hard because these guys can just stay where they are. And then this guy can move over to the other side, and he can stay right here. So we have 1 over y dy dx y plus 2 minus ln y dy dx equals 3x squared e to the x cubed times y plus 2 quantity squared plus 5 times y plus 2 quantity squared. On the left, we are factoring out a dy dx. So we have dy dx 1 over y times y plus 2 minus ln y equals, once again, 3x squared e to the x cubed times y plus 2 quantity squared plus 5 times y plus 2 quantity squared. Now dividing both sides by this 1 over y times y plus 2 minus ln y. And that will cancel, giving us dy dx equal to 3x squared e to the x cubed times y plus 2 quantity squared plus 5 times y plus 2 quantity squared, all over, I don't really need parentheses, 1 over y times y plus 2 minus ln y. And that is your final answer there. A lot of work, but it gets you there. What I will mention is that in the answer looks a little bit different, and it's because the y plus 2 quantity squared on the top has been factored out, and this fraction is written a little bit differently. So in the answer key, it'll say 3x squared e to the x cubed plus 5, and then the y plus 2, because quantity squared factors out since they both have one. And then on the bottom, instead of 1 over y times y plus 2, it's y plus 2 over y minus ln y, but it's the same answer. So once again, it glitched on me. I'm feeling a little uneasy about how this is going at this point because I have now had 2 large sections of this video glitch. I'm not going to redo this problem either. I don't even know if I want to bother talking through all of it again. Here's the first derivative. So you're finding a second derivative. Here's the first derivative. You find the second derivative using quotient rule. Then when you have a dy dx left, you plug in the dy dx from over here. And then I simplified it. So I will leave that on the screen for you to just kind of look at and enjoy. And if you want to dissect through that, then you can. I do not have the energy to redo this problem, and who even knows if this segment's going to save. All right, for number 11, let's keep our fingers crossed that this records. You're finding the equation of the line tangent to x squared y squared equals 9 at the point -1, 3. So for a tangent line, you're going to need an x value, a y value, and a slope. The x value and y value are given to us right there. So we have -1 and 3. For the slope, normally this would be like f prime, but it would be like f prime of x, f prime of whatever x value you have here. In our case, we're going to have an x and a y value to plug in. So the more appropriate way of writing this would be dy dx and evaluate it at the point -1, 3. So we're going to find the derivative and evaluate the derivative at -1, 3. So we will start by taking the derivative of x squared y squared. That's going to require product rule. So we have f and g. F is equal to x squared. F prime is 2x. G is y squared. G prime is 2y dy dx. So the derivative, f prime g, 2x times y squared, plus g prime, 2y dy dx, f is equal to the derivative of 9 is 0. Right? So I'm going to go ahead and move the 2xy squared to the other side, we have on the left side 2x squared y dy dx equals negative 2xy squared divided by 2x squared y you get some stuff that cancels, these 2's cancel. This x on top cancels, so you no longer have the x squared. This y on the bottom cancels, so you no longer have the square up there. It becomes negative y over x. We needed, for the slope, to evaluate this at the point negative 1, comma 3. So plugging in negative 1 for x and 3 for y. So we have negative 3 over negative 1, which is 3. So our tangent line will be y minus y1 equals m times x minus x1. So y minus 3 equals 3 times x plus 1. Y equals 3x plus 6 when you distribute and then add over the 3. Y equals 3x plus 6. All right, so for this problem, for number 12, I went ahead and screenshotted it because it's a lot easier to work with the screenshot. So we have a curve, and we want to find the equation of the normal line to the curve at the point 3, comma 1. A normal line is going to be the line perpendicular to the tangent line at the point of tangency, so at the point 3, comma 1. So for a line in general, we need an x value, we need a y value, and we need a slope. And normally this slope, right, for the tangent line would be the derivative evaluated at the point we were given. However, because it's the normal line, we want to find the perpendicular slope. So we want to find the opposite reciprocal of the tangent slope. So we're going to find dy dx, we're going to plug 3, comma 1 in. But after we do that, then we are going to find the opposite reciprocal. So we'll start with differentiating up here. It's going to give us 2x minus 8 plus 2y dy dx minus 6 dy dx. Derivative of negative 20 is 0. And then moving the 2x minus 8 over and factoring out the dy dx at the same time. We have dy dx times 2y minus 6. So what I'm doing is I'm leaving these guys over and I'm factoring their dy dx's out. Is equal to 8 minus 2x. dy dx is equal to 8 minus 2x over 2y minus 6. Now evaluating that at the point 3, comma 1. So plugging in 3 and 1. So we have 8 minus 6 is 2. 2 minus 6 is negative 4. So this will give us negative 1/2. The opposite reciprocal, so if our tangent slope is negative, then our perpendicular slope, our normal slope, will be positive. So it's positive and then flip the fraction. So sometimes we use this notation, like m with an upside down t on it, to mean perpendicular. So we make it positive and then the fraction gets flipped upside down. So that would be 2. X1 and Y1 were given to us right here. So you have y minus y1 equals m times x minus x1. Y minus 1 is equal to 2 times x minus 3. In slope-intercept form, we have 2x minus 6 plus 1, so 2x minus 5. For the part B of this problem, I think I'm going to just take all this and move it a little bit and maybe shrink it up if it'll let me. Oops, not like that. Okay, let me try that again. Grabbed all this, make it a bit smaller, move it up a little bit. Part B, find the second point where the normal line intersects the curve. Hint, your normal line will look like y equals mx plus b, right? This is our normal line. Try substituting mx plus b in for y in the original equation. So our original equation was x squared minus 8x plus y squared minus 6y. It's this guy up here, equals negative 20. So I'm going to rewrite that down here. Let me pull that up on my screen so that I can easily write that. So we have x squared minus 8x plus y squared minus 6y equals negative 20. And we want to find the second point where the normal line intersects this curve. And the hint is to substitute. We know that y is equal to not mx plus b, in our case, 2x minus 5. So we can take 2x minus 5 and plug it in the places where we see y. So doing a little algebra here, remember here, you're not just distributing the square, you'd have to FOIL this. So you're going to get 4x squared, you're going to get, let's see, minus 20x plus 25. Distributing the negative 6, negative 12x plus 30 is equal to negative 20. So let's combine together like terms. So we have an x squared and a 4x squared. That's going to give us 5x squared. For the x's, we have negative 8x minus 20x, so negative 28, minus 12x, that'll be negative 40x. Now, I want to add this 20 to both sides so that we have a 0 over here, because we're going to have a quadratic to solve. So we have 25 plus 30. That's going to give us 55 plus 20 is going to give us 75. We can factor a 5 out. So we have x squared minus 8x plus, what's that going to be? 15 equals 0. Factoring that, we have x minus 5 times x minus 3 gives us x equal to 5 and x equal to 3. Now our original point that we got, because we're trying to find the second point, the original point we had was x1 equals 3. So we already have this guy here. 5 is the next point, but we need to find our y value. And the easiest way to find our y value is to use this equation right here. So y is equal to 2 times 5 minus 5, which will give us 5. So we have the point 5, comma 5. All right, so the last 4 problems are going to be related rates problems. And these ones ask to round to 2 decimal places and include units. So for the first one, let's read it first. The area of a circle is increasing at a rate of 49.5 meters squared per second. Find the rate of change of the radius and circumference when the radius is 6 meters. So we should start by drawing a picture. We have a circle and its area is increasing. So we can kind of guess that it's like growing outward. And sometimes our pictures are useful and sometimes they aren't. But here's a picture. It's growing outward at a rate of 49.5 meters per second. That's about all we can actually draw there. There's a circle that's increasing. We can write down what we know and what we want to know. So what do we know? The area is increasing at a rate of 49.5 meters squared per second. So the rate of change of the area, dA dt, is positive because it's increasing, positive 49.5 meters squared per second. We want to find two things. We want to find the rate of change of the radius and of the circumference when the radius is 6 meters. So we want dr dt when, when r is equal to 6, and we want dc dt, where c is circumference, when r is equal to 6. So we need to let's start with finding a way to relate area to radius. The area of a circle is pi r squared, and that relates area and radius together, so we can then use the information we have. So we're differentiating both sides with respect to t. So the derivative of a would be dA dt. For pi r squared, it'll be pi 2r and then a dr dt. We can now plug in what we know. So we know that dA dt is 49.5, and we know that the radius is 6. So we plug in 49.5 for dA dt. And then for r, we're plugging in 6. So if we solve for dr dt here, we get 49.5 over 12 pi, which plug into your handy-dandy calculator because we need to know it rounded to 2 decimal places. I get 1.31, and then for units, it's in seconds, and then radius would be measured in meters, not meters squared, but meters, because radius is a distance. So this would be meters per second. And that was for the radius. So now we have a new fun bit of information we can put in our know column. We don't just know dA dt, we also know that dr dt is equal to 1.31 meters per second. And when choosing what things we need to relate to each other, we can now choose to use this information. So there's not a nice formula for relating area and circumference together, but there is a formula that relates circumference and radius together. So the formula that relates radius and circumference together is that the circumference is equal to 2 pi r. So if I differentiate that formula, that equation, sorry about that. Then we get dc dt equals 2 pi, and then the derivative of r is dr dt. Once again, we know that dr dt is 1.31 meters per second. So dc dt is equal to 2 pi times 1.31. And that gives me approximately 8.23, and then circumference is also measured in meters. And the rate of change would be measured in meters per second. right, for problem 14. An ice cube is melting such that the sides of the cube are decreasing at a rate of 0.3 inches per second. Find the rate of change of the volume of the ice cube. So I'm going to draw an ice cube because it's always good to draw a picture. It's an ice cube. It's melting, so it's going to be kind of caving in on itself. That's about all the picture I can draw there. We can talk about what we know and what we want to know. We know something about the sides of the cube. We know the sides of the cube are decreasing at a rate of 0.3 inches per second. So when we hear cubes, the cube means that all of the side lengths are equal. And when it says that the sides are decreasing, we can assume that that means side lengths. So the side lengths of the cube are decreasing at 0.3 inches per second. So all of these sides have the same length. We can call it x. And we know that dx dt, now it's decreasing, so it's negative 0.3 inches per second. Those side lengths are decreasing. We want to find the rate of change of the volume of the ice cube. So we want dv dt, and just in general. So it doesn't say at a particular time, we just want dv dt. We need a formula that will relate together x, which is our side length, and volume. And the volume of a cube is just its side lengths, all the length, width, and height multiplied together. In this case, x times x times x. So it's x cubed. We want to differentiate both sides with respect to t. So we get dv dt equals 3x squared, and then dx dt, because we have to do chain rule there. We know that dx dt is negative 0.3 inches per second. So we have 3, and then, so I had just realized we are actually missing vital information because we need to be able to plug in something for x. So this problem was actually missing a sentence here saying that this happens when the side lengths are 4 inches long. So when x is equal to 4. I'm editing that on the review right now, and I will save and upload that. So anyways, the information we have then, we have that dx dt is equal to negative 0.3 inches per second, and we have that x is equal to 4 inches, and we can plug that in. So we have 4 squared, dx dt is negative 0.3. So we have 3 times 16 times negative 0.3, negative 14.4. And now volume, if the side lengths are in inches, volume is in inches cubed, and then the time is in seconds. So the volume of the cube is changing at a rate of negative 14.4 inches cubed per second. All right, number 15. We have sand is draining out the bottom of a cone-shaped hourglass at a rate of 4 centimeters cubed per minute. The cone has a height of 10 centimeters and a diameter of 16 centimeters at the top. Find the rate of change of the radius of the sand when the height is 5 centimeters. So we have a cone-shaped hourglass, and let me draw a picture. Sand is draining out the bottom, so we can kind of guess it looks like this, with sand is draining out. And the cone has a height of 10 centimeters and a diameter of 16 centimeters at the top. And then we know that there's sand in here. I'm going to make my sand green, I guess. So there's sand in here, and the sand is draining out. Let's see, do we grab everything? So the sand is draining out. The cone has a height of 10 centimeters, diameter of 16 centimeters. Find the rate of change of the radius of the sand when the height is 5 centimeters. So what we know is that the sand is coming out at a rate of 4 centimeters cubed per minute. So the volume of this little bit of sand in here, the volume of it is decreasing. So the volume of that sand is decreasing at a rate of 4 centimeters cubed per minute. So the negative is because it's decreasing. We want the rate of change of the radius, so dr dt, when the height is equal to 5 centimeters. So we need to kind of label some stuff on here. So the height is going to be the height of the sand in here, and the radius is going to be the radius of that baby cone inside there where the sand is. So if I kind of take a cross section of this cone, where this is the radius, this is the height, we know this right here is 10 centimeters because that's the height of the cone, and that we know the diameter is 16 centimeters, but the radius would be half of that. So the radius of the big cone is 8 centimeters. And we can set up a similar triangles problem here, which we're going to need in a moment because we're going to relate volume and radius together, and we're going to end up having height. So we're going to use this in a second. Why don't I write down my formula to relate radius and volume? So the formula for the volume of a cone is pi over 3 r squared h. So the problem being that we have information about r, but we don't have any information about h, so we need to figure out how to get rid of h. We'll use our similar triangle setup over here. So we have r is to 8 as h is to 10, and you can cross multiply, so 10r is equal to 8h. And we want to get rid of h, which means we want to solve for h here. So I'll divide both sides by 8. And get h is equal to 10r over 8, or 5r over 4. We're taking this, 5r over 4, and we're plugging it in right here. So we have volume is equal to pi over 3, r squared, 5r over 4. So we have 5 pi r cubed over 12, or maybe you'd rather see it as 5 over 12 pi r cubed. Same thing. Either way is the same thing. Differentiating both sides with respect to time. We get dv dt is equal to 5/12 pi and then 3r squared dr dt. We know that dv dt is negative 4 centimeters cubed per minute. And we know that the radius, well, we don't know the radius. We know the height is 5 centimeters. So let me write down what we know again. Oops, there we go. So we know dv dt is equal to negative 4 centimeters cubed per minute. We can plug that in. We know that h is equal to 5 centimeters, but we don't need h, we need r. But the good news is we have a formula that relates h and r together. So h is equal to 5r over 4. So if the height is 5 we can solve for r. So 20 is equal to 5r, r is equal to 4. So r is 4, dr dt is negative 4. We get dv dt is equal to 5/12 pi times 3 times 4 squared times negative 4. Plugging that all into your calculator. Give me a moment to actually do that. You get negative 251.33, and then the units for volume should be, oops, and then I actually made a mistake here. Just make a mistake here. dv dt, I thought that this was an r because sometimes my r's look like v's. dv dt is negative 4, so this is actually negative 4 over here. So it's going to be a little bit different. You have negative 4 equals 5/12 pi, 3 times 4 squared. dr dt is what we are solving for. So dr dt is going to be equal to negative 4 over 5/12 pi times 3 times 4 squared. Plugging that into my calculator, negative 4, 5 divided by 12, pi times 3 times 16, I get approximately negative 0.06. Radius is measured in centimeters, so this will be centimeters per minute. And it would make sense that the radius is decreasing. So find the rate of change of the radius of the sand when the height is 5 centimeters. It would make sense that the radius is decreasing because sand is falling out of the cone. All right, last problem. So a pizza is cooking in the oven. It has a volume that is increasing at a rate of 13.1 inches cubed per minute and a height that is increasing at a rate of 0.05 inches per minute. Find the rate of change of the radius of the pizza when the radius is 12 inches and the height is 1 inch. Hint, think of the pizza as a cylinder. So we are kind of thinking of the pizza like it's a cake pan or something. So things that we're interested in are the height of the pizza, which I could label h. Maybe I'll draw that a little better. It's the h. And then also the radius of the pizza, which I'm going to label r. What we know is that the volume is increasing, so dv dt, because it's increasing, it'll be positive, and that's happening at 13.1 inches cubed per minute. And we know that the height is increasing, so dh dt, also positive, increasing at a rate of 0.05 inches per minute. We want the rate of change of the radius, so dr dt, when the radius is 12 inches and the height is 1 inch. So when r equals 12 inches and height equals 1 inch. So the formulas that we want that relate volume, height, and radius all together are going to be the volume of a cylinder. The volume of a cylinder is pi r squared h. We have to be careful here. So when we do this, because you have an r squared and an h being multiplied together, this is actually going to end up being product rule. So when we go to take this derivative, when we go to differentiate on both sides, we have to do product rule there. So f is equal to pi r squared. F prime, it was going to be pi times 2r, or sorry, not 2, yes. Pi times 2r times dr dt. G is going to be h, and g prime will be dh dt. So differentiating both sides with respect to time. We get dv dt is equal to, now it's f prime g, so this will be 2 pi r dr dt. That's f prime times g is h, plus g prime, so dh dt, times f pi r squared. The information that we have, we know that dv dt is 13.1. We know that dh dt is 0.05. We know that in our case, the radius is 12 inches and the height is 1 inch. So the radius is 12 inches, the height is 1 inch. And we can plug all those values in, and that will allow us to solve for dr dt. Now, we could move and get dr dt by itself to begin with, but it's honestly just easier if we plug in right away. So dv dt is 13.1 equals, so we have 2 pi, r is 12, and then I'm going to put h right now. So h is 1, and then dr dt, plus dh dt is 0.05 times pi times r squared, so 12 squared. I'm going to start by kind of simplifying a little bit here. So we have 13.1 equals 24 pi dr dt plus 12 squared times 0.05 is 7.2 pi. So I would subtract the 7.2 pi on both sides. And then to get dr dt by itself, I'm dividing by 24 pi. So we have 13.1 minus 7.2 pi all over 24 pi. Plugging that in my calculator, I get negative 0.12 or 13. Now that doesn't sound right. That doesn't sound right to me. It doesn't sound like the radius should be getting smaller as the pizza is getting bigger. So something went wrong here, and I need to take a moment to figure out where that something went wrong. So, no, it is the right answer. So this is the right answer. And then our units here are going to be inches per minute. The best explanation I have for this is you could think that, like, as it's getting, like, taller, it's, like, shrinking in on itself. Not sure, but this is the answer. So most of the time these answers make a lot more sense than this. This one just doesn't make as much sense. But it is the correct answer. The radius is actually shrinking. So anyways, that's the entire review. Sorry I wasn't able to finish it in one sitting. I know it's already really, really long, but hopefully that was useful. If you have questions, send me an email.